So yesterday almost you have completed the strain energy. So you have to discuss some more question, then we'll go for the thermal stresses. I hope you have done all the questions yesterday, whatever is given in the workbook. What was the question? What was the conclusion was made at the end of the class now? Whenever at any cross section more than one axial load, more than one shear force, more than one bendiment, more than one twistment, there you cannot use the superposition principle. There you have to go for always the integration method is going to be required now. And in the chapter number 2, I hope you have completed all the questions. Only some new terminology is going to be viscoelastic. In question number 10 and chapter number 2, question number 10 and chapter number 2, there is one word is called the viscoelastic. Viscoelastic is the time-dependent elastic deformation. Time-dependent elastic deformation. Viscous plus elastic. We are all dealing with the perfect elastic. Perfect elastic means if I am going to pull it, sorry. Perfect elastic means if I am going to pull it and if you remove the load, it will come back to its original position and it will regain the original shape and dimensions immediately. But if the same spring is kept in a viscous fluid, same spring is going to be kept in a viscous fluid. If I am going to pull it, it will elongate. If I remove the load, but it will come back to the original position, but it will take the some time. Because the resistance due to the viscous fluid, it will offer some resistance to the deformation. So it will not come back to the original position immediately. So viscoelastic means time-dependent elastic deformation. Time-dependent elastic deformation. But best example is going to be what now? Door closers. Generally, if I am going to push a door, it will open. If I remove the load, it will come back immediately. It will come back immediately. It will come back immediately now. But on the back side, if I am going to provide a viscous damage, generally automatic door closers are going to be there now. If I am going to push it, it will open. If I remove the load, it will come back gradually because back side what? A viscous damper is provided. So it will not come back immediately. It will gradually come now, gradually come. But if there is no viscous damage, generally some doors, generally most of the doors, there is no houses, etc. Mostly, if I am going to push it, it will come back suddenly now. Because there is no viscous damper now. Spring damper is not provided the back side. But automatic door closers, if you push it, it will come back gradually. Means it will take some time. So that is the example for viscoelastic. So viscoelastic means viscoelastic materials are those materials. Viscoelastic materials are those materials which exhibit time-dependent deformation. Time-dependent elastic deformation. Viscoelastic materials are those materials which exhibit time-dependent elastic deformation. That one word is missing now. That are not discussed because we are dealing with the perfect elastic. Next, there is one word is called the tenacity. Tenacity is the ability of a material to withstand the more tensile load. Tenacity is the ability of a material to withstand the more tensile load. This word is used in case of question number 5. Question number 5, one word is called the tenacity. Tenacity is the ability of a material to withstand the more tensile load. Next, one word is the creep. Creep I have not discussed. Creep is going to be studied in the material science. But this question is included in the creep in this workbook now. What the creep definition now? Creep is a plastic deformation, not elastic deformation. What the creep definition now? Creep is defined as the slow and progressive. Creep is defined as the slow and progressive permanent deformation or plastic deformation of a material at elevated temperature under constant stress. Creep is defined as the slow and progressive permanent deformation of a material at a elevated temperature under constant stress. Most of the times, elevated temperature word is not going to be given now, but the one word is going to be required now. And constant stress. You have studied the creep curve, you have studied now. But most of the textbook, they are giving the constant load. If the load is constant, stress need not be a constant. So actual word is about now, constant stress. But if you see the workbook options now, creep is given as what now? Plastic strain with a time at a constant load. So it is not the actual definition, but our aim is to what? Identify one of the correct option, that's all. Out of the given option, which is more justified, that you have selected. That's why I'm clearly mentioned, don't build your definition based on the questions and the options now. Don't define the creep as what in the workbook? Plastic strain with time at constant load. Some teachers are going to be directly what defining the, explaining the subject, building the concept based on the questions now. We should not build the concept and definitions based on the questions or options. Our aim is to what? You should be thorough with the actual definition, actual concept. Using that one, you have to go for the question. By using the concepts, you have to solve the question. But vice versa is not correct now. From the questions, don't try to build it now. Sir, you mentioned a constant stress, sir. Workbook is given constant. That is what now? That is not about a definition. Your aim is to what now? You are appearing for exam. Out of the 4 options, you have to identify one of the correct option. Suppose if you given one option in none of the above, you have to select the none of the above only. So once again, we're defining the creep now. Creep is defined as the slow and progressive permanent deformation of a material at elevated temperature under constant stress. So these are the 3 words are required now. These are the 3 words are required. And one question, the doubt is going to be question number 3. Chapter number 2. So the maximum strain energy stored in a body without elastic exceeding the limit of proportionality. Answer is what? Proof resilience. Some students are, sir, you mentioned proof resilience is the maximum energy absorbed by a component within the elastic region, and we are given, it is given by area of the load versus deformation curve up to elastic limit. Sir, in the question proportionality limit is given, but what is used now? Maximum word is given now. Since the maximum word is there, you have to select the proof resilience. If there is no word of maximum, then you have to go for the resilience now. Some students are what now? Sir, you are given the definition as proof resilience, the maximum energy that a component can what now? Absorb within the elastic region. Maximum energy absorbed by a component within the elastic region. And it is given by area of the load versus deformation curve up to elastic limit. But in the question is given limit of proportionality. So it should be a resilience, sir. And you have mentioned load versus deformation curve within the elastic limit. Area of the load versus deformation curve within the elastic limit. It is given by resilience, sir. Then answer should be A, but you are given option B. Since the word is given as maximum, then you have to go for the proof resilience should be considered. If that word maximum is not given, then you have to go for the resilience. Already mentioned, for most of the materials, elastic limit and proportion limit are very close. elastic limit is slightly greater than the proportional limit. The difference between these two is what now? Very, very small. Similarly, in the questions, they are giving the Hooke's law valid up to elastic limit, Hooke's law valid up to proportional limit. But generally, they are giving the elastic limit because they are very close. So you have to see the question and which is more appropriate, that you have to select it. And you can see the question number 15. Option A is representing elastoplastic. For option A, write down this is representing, already first day you have studied now, rigid body, perfect rigid body. Is a stress strain curve for perfect rigid body. This is for when you are studying the first day, difference between the strength of material as well as engine mechanics. This you called the perfect elastic. In place of the perfect elastic, what you can call it? The perfect brittle material. Perfect elastic. In place of the perfect elastic, you can call the perfect brittle material. What is the meaning of perfect brittle material? There is no plastic deformation. So this has the only elastic. Strictly speaking, this is about a perfect elastic, but this can also be considered perfect brittle material. This is for perfect rigid body. These are all idealized condition. These are all not practically possible. Idealized condition. Ideal condition, ideal bodies or ideal materials, you can call it now. This is for perfect rigid body. Stress strain curve for perfect rigid body. This is for perfect elastic. Or perfect brittle material. How it is what, sir? How it is the brittle material? Brittle material means what you have studied. A perfect brittle means there is no plastic deformation. Cast iron is not a perfect plastic. We already shown the cast iron. In cast iron, elastic and little bit of elastoplastic. Total deformations are 3: elastic, elastoplastic, and plastic. Perfect brittle material means only elastic deformation. That's why it is called as what now? Perfect elastic body or perfect brittle material. This is this portion is similar to just like yielding region. In yielding region, what the stress strain curve horizontal line. So what that yielding region is representing now? Yielding region is the region where material will exhibit considerable plastic deformation for a constant value of the stress curve, for a constant value of the load or the stress, constant value of the load. Same thing here, what now? Here what now? Stress is constant, but it is undergoing about a plastic deformation. If I remove the load, it will not regain the original shape. So this is what now? Perfect plastic. Perfect plastic. Mean for a constant value of the stress, it is exhibiting about now plastic deformation. This is default, this is a longier strain. So this is called as what now? What the difference between these two now? Here y coordinate is 0, means stress is 0. This is called as the ideal plastic. Ideal plastic means without applying any load, it is undergoing a considerable plastic deformation. Ideal plastic. This is a perfect plastic and ideal plastic. Ideal plastic. This is almost what a reverse of the rigid body. Rigid body, there is no strain, but stress is there. But here there is no stress, but the strain is there. This is what the ideal plastic. This is for elastoplastic. For elastoplastic is a combination of these two. Elastoplastic. Is the elastic, and this is what now? Just like strain hardening. In the strain hardening region, what happens now? If you see the stress strain curve of mild steel, yielding region will be there. Once again, the curve will increase. In the strain hardening region, what is the strain hardening region now? Once again, the y coordinate will increase. So this representing what? A strain hardening. So this is what now? Linear strain on. So it is called as what? A elastic material with linear strain hardening. Linear strain hardening. And if this given as a curve is given in place of the inclined line, if the curve is given, then it is what now? Elastic with non-linear strain hardening. Non-linear strain hardening. So these are the stress strain curve for ideal bodies or ideal material. So these are the two questions asked in these two now. Second one and the sixth one asked in the gate paper now. That is the only workbook question is given now. Perfect brittle material like ceramics is given now. What is given in the question of which one of the following stress-strain relationship behavior of brittle materials such as ceramics and thermosetting plastics? Ceramics and thermosetting plastic. So 4 curves are given now. Then which curve you have to select it now? This now. So option D is correct now. Option D. In another question, in the workbook question, what is given? A material is given, asked to identify which is the appropriate stress strain curve. But another question, what another paper they asked what now? This stress strain curve is given and represents the stress strain curve shown in the figure, representing elastic material with linear strain ordering. Elastic with linear strain ordering. So these are all ideal conditions. So in the workbook question now, for the question number 15, chapter number 2, answer is D. Answer is D. But for option A, write down within the bracket, option A within the bracket, elastoplastic. So many times I mentioned, first identify the correct option. For the given question, answer is D, 15th question. Then you check the ABC. Option D is correct now. Then check the ABC. A is representing elastoplastic. A is representing elastoplastic. B is representing elastic material with linear strain ordering. B is representing elastic with linear strain ordering. C is representing perfect plastic. C is representing perfect plastic. A is representing elastoplastic. B is representing elastic material with linear strain ordering. C is representing perfect plastic. And option D is representing perfect elastic or perfect brittle materials. And the question number 21, in question number 21, answer is 3.646. You have to do the integration, you have to do it now. But small data is missing. Question number 21. But the units is going to be megapascal. These units are missing now. Units write down now, megapascal. Then only answer is correct now. So this is missing in the input data. Add this megapascal. Then answer will be, answer is 3.646. If it is a pascal, this answer is not correct now. So whatever I have given, the answer is 3.646 is valid when the stress units are megapascals. So in the option, in the input data, add this now. Megapascal, then answer is 3.646. You have to do the integration. So remaining directly can do it now. And this is a very standard question also, interviews now. They will ask to draw the stress strain curve of a mild steel under tension test. Draw the stress strain curve for a mild steel under tension test. Then mark the salient points, important points on the curve. Explain their significance. Explain their significance that you have studied. Proportion limit significance, elastic limit significant, yielding region significance, strain hardening, necking, ultimate point, all the significance you have to explain now. Then they will ask, draw the stress strain curve for a perfect elastic material, perfect brittle material. So this type of, this data is going to be required, this information required now. But gate paper, they have given the 2 questions are given on this, not till now. What is the strain energy of this bar now? The strain energy of the bar. If I take a section, how many axial load is there? Only one axial load. Axial load is a constant. One twistment, then you can add it. Here only everybody, sir, you are doing the superposition. Superposition principle is not valid when more than one axial load is there. Only one axial load and one twistment. So strain energy due to axial load and strain energy due to twistment can be added. Sir, this is a normal load, sir, this is a shear load. Stresses cannot be added. Stress is about a tensor. But strain energy is about a scalar quantity. Strain energy is nothing but a work done. Work done is a scalar quantity. So the strain energy due to axial load and strain energy due to twistment directly can be added. But stress cannot be added, strain cannot be added now. And deformation cannot be added. But strain energy can be added now. It is not a superposition principle. Strain energy due to two axial load, they cannot be what now? Added now. So here directly what? If I take a section, how many axial load is there now? One axial load, one twistment. So what is the strain energy you have to write down here now? Strain energy due to pure axial load. And strain energy due to pure torsion. So directly what you are doing now? Clearly mention superposition principle is not valid. Strain energy due to two different axial loads cannot be added. Yesterday at the end of the lecture you have studied now. Self-weight and axial load strain energy cannot be added. But here what? Only one axial load is there, constant. One twistment is there. So you can add it now. So what is the equation now? P square L by 2AE. T square L by 2GJ. Mostly they are asking in terms of the load only, in terms of load and areas. But if you ask in terms of the diameter, but in the question G is not given, every material E is known now. So in place of G, what do you write down? E by 2 into 1 plus mu. So you can do the further simplification as per the given options now. Sometimes you can, this is what in terms of the load. Sometimes they are asking in terms of the stresses. In terms of the stress, what should I write down here now? In terms of the stress, if I am going to multiply and divide by the volume, if I multiply and divide by the volume, multiply and divide by the area, A square, P square by A square is nothing but what now? P square by A square is nothing but the axial stress. So it is also equal to what the other way you can write down now? Under pure axial load, you can write down P square L by 2 AE, or you can write down Sometimes they're asking in terms of the axial stress. Sigma A square by 2E into volume. What the axial stress? P by A. Similarly, under pure torsion, this is under pure axial loading. Similarly, under pure torsion, T square L by 2 GJ, or it is in terms of the torsional shear stress, tau T max whole square by 4G into volume. Once again, how to get it now? In place of T, what should I write down now? Pi by 16 d cube into tau permissible. T is equal to what? Zp into tau permissible. Zp into tau T max. What the tau T max equation? T by Zp. How you got it? Mean what you have to do it now? T should be replaced by Zp into tau T max. In place of T, write down the Zp into tau T max. For a solid circular cross section, what the Zp? Pi by 16 d cube. So simplified, you are going to get this now. But in all the textbook, they are writing the 4G, the 2G. 2 into G. 2 into G is valid under direct shear stress. That is when tau D is there, when a shear force is there. Most of the textbook, they are writing tau square by 2G into volume. The 2 is valid when a direct shear stress, that is when shear force is there. When a shear force is there. So sometimes they are asking in terms of the stresses. So if you ask in terms of the stresses, you can write down now this you can further simplify it also. In place of G, what you can write down now? G is equal to E by 2. So you can take out the which one as a common? Now volume by 2E can be taken as a common. This is valid under constant axial, pure axial load. This is under pure torsion. This is under constant shear force. There is one block example. Block example, this is all valid. Yesterday I explained in terms of the load. But if you ask in terms of what the tau D? Tau D means P by A. Here what the sigma A? P by A. What the tau T max? T by Zp. That is 16 T by pi d cube. And here tau D means P by A. Most of the textbook there, but this is valid here. Direct shear stress is the torsional shear stress. So you should be careful. You should be careful. Under pure bending. Under pure bending, what the equation is written now? M square L by 2 EI. M square L by 2 EI. This under pure bending m square L by 2 EI. Now if you write down what the sigma B max in place of m, what should I write down now? Sigma B max into Z. M is equal to sigma B max into Z. Z is equal to I by Y max. But this equation what is neglected now, whenever shear force bending is going to be there now. So this is by neglecting the bending moment. Strain energy due to bending moment. This is under constant axial load. Pure axial loading, you know, pure torsion. This is a pure bending, but there is no pure shear force condition. There is no pure shear force. That's why never I use the concept of pure shear force. Whenever a shear force there, automatically what a bending moment varies. Bending moment is one order higher than what now? Bending moment is one order higher than shear force variation. So here bending moment effectiveness, when you are studying the what now? Block example, when you are studying the shear strain example, when a block is subject to shear force, you have studied what the block is distorted. The distorted shape is possible by neglecting the bending moment. So this equation is valid by neglecting the strain energy due to bending moment. Pure bending means bending moment is constant. Whenever a shear force 0, bending moment is constant. Whenever a shear force 0, bending moment is constant. Or when bending moment is constant, shear force 0. But when shear force is constant, bending moment is not 0. Clearly stated bending moment variation one order higher than shear force. So vice versa is not valid now. When bending moment is constant, shear force 0. But vice versa is not correct now. That is when shear force 0, bending moment is, sir, when shear force constant, bending moment is 0 is not valid now. Pure bending means bending moment is constant. When bending moment is constant, shear force 0. But reverse is not correct now. When shear force is constant, bending moment is 0. That is not correct now. When shear force is constant, bending moment is not 0 now. Bending moment is non-zero. Whenever shear force is constant, vice versa means what? When shear force 0, bending moment is constant. But reverse is what? Now we cannot mention like this now. When shear force is constant, bending moment is non-zero. Bending moment is not. That's why you have studied whenever a shear force there what now? Bending moment always will exist. Now this example you have studied now. Shear force W, bending moment is what? W into X. Bending moment variation is one order higher than shear force. Here shear force is what? A constant. Therefore bending moment is what? A linear. So here we are assuming the shear force a constant. If the shear force a constant, then automatically bending moment will vary linear. So that you are neglected. Here axial load is constant. Here twist moment is constant. Shear force constant. But when shear force is constant, bending moment is not going to be 0. Bending moment is a non-zero. But when bending moment is constant, shear force 0. %95 of the textbook they will write down always 2 into G. They will not write down tau D and they will not write down the tau T max. Simply under shear force they will write down what now? Tau square by 2G. The 2G, whenever I written the 2G means it is a direct shear stress. That is when you are going to get a direct shear stress, when a shear force is there. But whenever it is about a twisting, torsional shear stress, then the constant is 4 into G. But this is valid for what now? Circular. This is valid for circular. But same thing if the solid circular, but if it's hollow circular, in for a hollow circular, same equation but 1 plus k square. What the k now? Ratio of inner diameter to outer diameter. I'm not preparing the summary table. Now you can prepare the summary table. Now you can prepare it now. So I want to, because by Monday I have to complete the syllabus. Still I'm lagging about now 5-6 hours. Somehow I have to maintain the 5 hours maybe lagging now. I need around 40 hours, but Monday I'm going to get the, even if I take the 310, I'm going to get the 7 hours. 7 into 5, 35 hours is going to be there now. I can complete even 25 hours also can complete it now. I can tell Strenergy is completed. Strenergy completed, you can do it now. I can skip it like this. Even 20 hours also I can complete it. If I want to what now? Complete the remaining portion also just like what you have studied thoroughly. Then I need at least 40 hours is required now. So I need a almost shortage of 5 hours is required. So mostly I'm planning Saturday, Sunday, like that we are going to extend the 1.5 hour. We'll take a break directly at the lunch break will be given 12:30, directly 8 to 12:30, and 1:32 we'll have the 5 o'clock we'll have the session, so that I can able to complete. I'm planning now. We'll see that we are going to decide last 2-3 days. We are going to decide it, because from 17th onwards new subject is going to be started. That is the deadline they given to me now. You have to complete by 16th now. So that's why I written this one. Now you can prepare the tabular form. Otherwise, if possible, I will upload that summary table now. Stress cannot be added. Normal stress and shear stress cannot be added. Stress is about a tensor. Tensor is about a second order vector. Tensor is about a stress is about a second order tensor. Depend upon the two directions. Stress cannot be, normal and shear stress cannot be added. But here these two strain energies can be added because it's going to be a scalar quantity. What is the strain energy under this case now? It is eccentric axial load. Every eccentric axial load equal to one axial load and one bending moment. Axial load is constant, bending moment is constant. Then you can once again add it now. So it will be equal to Now if I take a section, once again only one axial load constant. Axial load is a constant. Then I can use the P square L by 2 AE. And what about the bendiment? Now PD by 2. Bendiment is also constant. Then you can use which equation? P square L by 2 AE and this one now. Strain energy due to pure axial loading. Don't write down the prismatic bar, pure bending. Here pure bending, pure axial loading now. Most of the time we know the load, but sometimes they are asking in terms of the stresses equation, or sometimes directly the stress is going to be given. If this question directly there, a shaft is subject to pure torsion, maximum torsional shear stress 100 megapascals. Find out the strain energy. Everybody is going to 90% of students they are going to use this equation, except the student who has attended my class. They are going to give the correct answer. Otherwise, what now? 90%, because all the textbook they are giving like this only. Check the simplification. You are going to get it now. Here not neglected because bendiment is constant, shear force 0. Check the simplification now. But the moment of inertia pi by 64 d to the power of 4. So 2 by 64, 32. And what the bendiment of P d by 2. So 1 by 2 whole square means 1 by 4. 32 by 4. So you are getting 10 P square L by pi d square E. All the units are what? Newton meters or you can write down the joules now. So in this case, how many loads are there? Now one shear force and one bendiment. But whenever a bendment is there, shear force is going to be neglected now. The strain energy due to shear force is very smaller. The strain energy due to shear force is very smaller in comparison to it. Here, how many loads are there now? One shear force, constant. And what the bendment now? Two bendments are there. W yesterday I explained now. So here, most of students they are going to do like this now. Here, superposition principle is not valid. Superposition here, how many bendments are there now? Two bendments. One is varying, one is constant. Yesterday I already explained. Here you cannot use the one shear force is there. Two bendments are there. So here you have to use the strain energy due to shear force plus strain energy due to bendment. One shear force and one bendment will be there now. But this is neglected. Whenever a bendment is there, what the strain energy due to shear force is very smaller in comparison to bendment. Whenever it is mentioned as a beam. Beam means length is very large, cross-sectional dimensions are very small. So this is taken as suppose if only block is there, then in that case we are going to neglect the strain energy due to bendment. Only are consider strain energy due to shear force. Block means what? A block subjected to shear force. In that case we are going to neglect the strain energy due to bendment is neglected. So here, how many bendments are there? No, two bendments. So here you have to go for the integration. 0 to L, what the bendment equation now? So complete this integration now. But most of students they are going to give the answer like this now. They will assume like this now. And in this case, yesterday work done concept can be used now. They will do the work done what the strain energy are written here now. W square L cube by 6 EI. And here M square L by 2 EI. They will add it. We are going for the integration WL plus WX, but most of students they are going to do like this now. Here strain energy is a U, U1, U2. So they will write down the what U is equal to U1 plus U2 under W square L cube by 6 EI. It is incorrect now. This principle is not valid. What is the reason now? Two bendments, one is varying, one is constant. We cannot add it now. So you have to go for the integration now. Strain energy due to axial load can be added to strain energy due to twistment. Strain energy due to twistment can be added to strain energy due to bending. But strain energy due to two different axial loads. Strain energy due to two axial load means one is varying, one is what, a constant. Here also what, strain energy due to two bendments, one is varying, one is constant. We cannot use the superposition. There are two bendments are there, one is varying, one is constant. We cannot use it now. But strain energy due to two different loads can be added. Strain energy due to two different load acting on the cross section can be added. Strain energy due to shear force and strain energy can be added. But why you are not, because it is very small, it is neglected. Whenever is mentioned the beam, it is going to be neglected now, shear force. So I taken as a generalized case. Here how many loads are there now? Axial load is there, self-weight is there, constant point load is there, bending couple is there, twisting couple is there. This is not possible for objective now, but I have given that to be safe side. So here if I take a, always what do you do it now? Take a section. So many loads are there now. What the axial load at XX? W plus WX by L. So for axial load you cannot use the superposition. Next. Shear force W. If it is given as a bar means what now? You have to consider strain energy due to shear force can be added now. Bar means what now? But B means what now? You have to neglect it. Next. Now what is the bendment equation now? WL plus WX. Then once again you cannot use the superposition for the bendment now. You have to go for the integration. And what the twistment now? Is it anti-clockwise, clockwise now? Anti-clockwise. Is anti-clockwise, clockwise. Anti-clockwise means is a horizontal plane. Then thumb is upward. Therefore double arrow is upward. The plus T or minus T. Plus T. So now what you have to do it now? This is varying. Varying. So now, strain energy due to axial load, strain energy due to shear force, by chance if it is given as a what, sorry, it is not shear force, this should be a bar. By chance if it is given as a beam, by chance if it is a give beam, this you neglect it now. By chance if it is a given beam, this you can neglect it. So now you can come, now this will be clear now. All the loads are there. Only one twistment constant, then you can use the pure torsion, T square L by 2 GJ, shear force constant, and a constant shear force for the strain energy, W square L by 2 AG. But two axial load, one is varying, one is constant, then you have to go for the integration. Two bend moments, one is constant, one is varying, you have to go for the integration. This you can simplify it now. This is not M, this is WL. What the bendment value now? WL. So I already written, but here I made a mistake now. M I written now. Today and tomorrow I am having the mains class at evening 5 o'clock. So tomorrow I am going to be what now? Somebody is suggesting today onwards you can take up to 12:30 and 1:30 to 4:30 like that they are giving the session now. But today and tomorrow I am having the mains classes there. So it is not possible to plan like this. We'll see. Tomorrow we'll see the what some idea will be there based upon that how much time is required. Then Saturday, Sunday, Monday we'll try to change the schedule now. My dear friend, here already written WL plus WX. By chance, if I written M, you have to understood that is a small word, small mistake. Already I have given the bend moment, I have written WL plus WX. By chance, if I written what now M I have written, you have to do the modification. What the bend moment now? WL plus WX. That is substitute it now. Clearly mentioned in beams. If clearly mentioned in a beam, always the strain energy due to shear force is neglected. By chance the same question is given, what a beam is given, then you neglect the second term, should be neglected now. Strain energy due to shear force is neglected. But which stress should be added now? Axial and bending stress should be added. Stress due to this should be added. Axial and bending stress should be added. That only a study. Critical point is the point on the cross section where resultant of axial and bending stress is maximum and resultant of torsional and direct shear stress maximum. Stress due to shear force and stress due to twist moment is added. And stress due to axial load and stress due to bend moment is added. Normal and shear stress cannot be added. Here only it is what now? Sir, you mentioned you should not, but this is what, try to remember the scalar quantity. Strain energy is the scalar quantity. The work done is the scalar quantity. So this example will clear all your doubts now. When you have to go for the integration, when you have to go for the no. Especially the strain energy due to bend moment is very important when you are going for the deflection of the beam. When you are going for the deflection of the beam chapter, there is one method is called about a Castigliano's theorem. Castigliano's theorem. Under Castigliano's theorem, the deflection and slopes are determined based on the strain energy due to bending moment. So in the Castigliano's theorem, the first step is to you have to find out the strain energy due to bending moment. If I am going to differentiate this term now, partial differentiate this strain energy with respect to bending moment, then it is going to give the deflection. In the Castigliano's theorem, this is itself a Castigliano's theorem. The deflection is going to be given by partial differentiation of the strain energy due to bending moment with respect to constant point load. W is the constant point load. And similarly, want to get a slope. You have to differentiate the strain energy due to bending moment. Partial differentiation with respect to bending couple or constant moment. W is about a constant point load. M is the concentrated moment. M is the constant moment. So whenever you want to find out the slope and deflection as per the Castigliano's theorem, first you have to find out the strain energy due to bending moment. Then first you have to write down the bending moment equation now. First you have to write down the bending moment equation, then you have to substitute in that equation, then you have to do the integration now. So complete this portion now. I have already given the diameter, I have given now. Area pi d square by 4. Here also pi d square by 4. What the I? Pi d to the power of by 64. And j pi by 32 into d to the power of 4. And in place of g, you can substitute e by 2 into 1 plus mu. In place of g, you can substitute e by 2 into 1 plus mu. the tabular form, I've already mentioned summary table. I'm not writing. Either tomorrow or today, any 3 days, I will come to the class 15 minutes before the time, 7:30 or like that. I will try to prepare a table, then you can take it directly, you can copy it afterwards now. Otherwise, if it is not possible for me to come to the class 7:30, then class will start at 8 o'clock only. Meanwhile, what now? To save some time, your time and my time, but I will come what now personally. My time is going to be wasted, but teaching hours are going to be what now? It's going to be reduced now. So I will prepare a table on the board. So once the class is going to be started at 8 o'clock, you can look at this one. Then afterwards, when you are doing the revising now, you can go through the recorded lecture, then you can copy the table. Otherwise, if it is not possible for me to come 7:30 or like that to prepare the table on the board, it will take at least half an hour time, it will take it now. Then you have to copy it, it will take some time now. Otherwise, I will ensure that the table will be uploaded. So anyway, some tables, what now? Deflection, standard deflections equations and theories of failures on summary table. That will be uploaded by today or tomorrow. It will be uploaded because the deflection equations has to be remembered now. So standard deflection equations for all the standard loading conditions: beam, maximum shear force, maximum bending, maximum slope, and maximum deflection. So the table will be uploaded one day before your deflection of the beam chapter now. And if possible, the SFD BMD conclusions also I will upload it, so that at least we can save some time now. So meanwhile, if anybody want to prepare the table, you can prepare it. I will also prepare it. Then you can modify it now. How you are prepared, myself I have written on the summary table. Then you can check it now. So the similar question yesterday, probably in the workbook I have given one question, that is a gate question. In that case, this was not there now. Only one twistement is there. So here which condition not satisfied now? This type of question torsion you have done it now, where you have calculated the maximum torsional shear stress angle of twist. Now you have to find out the strain energy. To find out the strain energy twistement, here to here what now? It should be treated as what, two shafts in series now. Here to here what, a prismatic, circular and pure torsion, and here to here prismatic, circular and pure torsion. So you have to use the t square L by 2gj 2 times now. Your twistment is constant. What the twistment now? T. What the twistment here now? Minus t. Is a plus t. This is what now? Anti-clock. This is a plus t. Clockwise the plus t. Otherwise double arrow is going to be towards left. But when you are doing the strain energy calculation, whether you take this plus or minus will not make any difference. Why now? Whole square term will be there. Actually, as per our notation, this is a plus t. Suppose somebody comes a minus t, it will not make any difference because whole square term is there. So in the strain energy calculation, you need not follow the sign convention. If I taken some, actually this as per notation a plus. Somebody has taken minus, it will not make any difference. This is a minus means this will plus. So final answer will remain same now. But anyway, everywhere I am following the same procedure. Either you can use the section method or you can use the talk diagram. Already a thorough. I am using the talk diagram here. Talk diagram is optional, but for the practice I am taking this now. So it is going to be T. Here no method is required. Why no? Directly what the twist element AB minus T, what the twist element BC plus T. When the methods are required now, when more than two members are there, only two members are there. AB member, what the twist element now? Twisting couplet A is going away minus T. For BC, twisting couplet C towards plus. So this is also not required now. Means circular and prismatic and pure torsion. Circular and prismatic and pure torsion. Then you can use the T square L by 2 GJ 2 times now. Thank you, my dear friend. but definitely some students at the end always what I know, but I will not bother, but I am telling now, in every batch 10% of a category they will give a, if the generally what offline batches maybe they will take the feedback. I don't know whether your online batches that they take feedback or not. In offline batches at the end of the subject when the median is taken the feedback, 90% they are going to give excellent feedback, but 10% or 15% students are going to be few students. Sir has taught excellently but it's taken more time. बहुत ज़्यादा टाइम लिया था और सर ने हिंदी में नहीं बताया था, कुछ जोक भी नहीं डाला था क्लास में, and used to take more hours. They will tell it, but I will not bother now because never they are not going to get a success. I will not get anything, my dear friend. I'm not getting what, even if I take the 50 hours more or 60 hours more, 50% or 60% more, I'm not going to get anything. My intention is the students who is attending my lecture, my class lecture notes, they should be sufficient. They need not depend upon any of the textbook, because for my students the time is a constraint. Within that given 8 months they should complete the complete preparation. For them concepts are required, problems are required, so the my notes should be sufficient. Some students are believing on me, so I should be my satisfaction only the students who is attending my lecture, they should able to do any of the questions without wasting their time. The class note should be sufficient. That is only my intention. I may waste my time now, but I should save my students' time. That is my intention. Self-satisfaction is important now. But some students definitely they will give the feedback. Definitely I'm not bothered. Definitely सर ने हमको लंच टाइम भी नहीं दिया था, सर के वजह से हमने 4 बजे 5 बजे खाना खाता था. ऐसा भी वोट ना फीडबैक दे सकते हैं अपने, बट आई एम नॉट बॉदर ना. I'm not telling what generally, these are all generalized comments. 10% category. सर ने एक सीक्वेंस में नहीं बताया था, वर्कबुक से सीक्वेंस से नहीं बताया था, टेक्स्ट बुक सीक्वेंस से भी नहीं बताया था, पूरा एक सीक्वेंस में नहीं बताया था. They will also write down, but definitely what now, I will least bothered, because for me that the 90% students are important. The 10% I'm not going to be bothered now. I hope this constant is okay. 16 into 17 is okay. अब this is, I hope this is constant, correct now. 16 into 17. What the 16 into 17 now? $272. $272. Completion of the syllabus is very easy. Completion of the syllabus is very easy. without knowing to what editing. The synergy, our topic can be completed 1 hour. I can complete it now. Almost I have taken the 5 hours time now. So like that, what each and every topic, what now? For synergy itself, I have taken 4 hours than what other teachers now. When you want something, we have to sacrifice something now. But you are not sacrificing. I am sacrificing myself now. Definitely, definitely they will understood. They are going to be what now? They are going to realize definitely now. But only few category will be there. And once I am telling, these are all not with respect to any of you. Only few categories, few students are there in every batch. Every batch will be there. With respect to them, I am telling now. Whether you give what, even if the maid is taken feedback, you give the worst feedback, I am not bothered now. I know what I am teaching for the last 25 years and what the students feedback is known to me. That is for my important now. I am not bothered about your 10% of the students now. So right on the next one, we'll complete the quickly. The impact loading also will complete it. Questions on the impact loading. So we'll complete the impact loading also. Problems are impact loading. Yesterday I studied the impact loading, you studied now. Okay. So directly I am coming to the, generally this should be discussed in the machine design. All dynamic loading should be discussed in the machine design. But the machine design teacher is going to leave this one. So that's why I have to cover this impact loading in the strength of material itself now. Okay. Steps used while solving the impact loading problems. Directly I am going for the examination point of view. Yesterday I already explained what the impact loading now. What should be the first step now? Questions are simple. Your aim is to once again you have to find out the impact stress strain deformation. Simple one word now. If you want to find out any parameter under impact loading, find out any parameter under impact loading, that is stress, strain, deformation, even strain energy also. What do you have to do it now? Any parameter under impact loading, that stress, strain, deformation, impact loading. is equal to corresponding parameter under static loading. Corresponding parameter under static loading multiplied by impact factor. Any parameter under impact loading is equal to corresponding parameter under corresponding static load multiplied by impact factor. Suppose if I want to get the impact stress under static loading, impact stress under axial loading. If I need the impact stress under axial loading, then what I have to do it now? Take the static stress under axial load. Multiply by impact factor. Similarly, if I need the impact bending stress, then what I have to do it now? Take the static bending stress, multiply by impact factor. Similarly, we want to find out the impact torsional shear stress. Then take the static torsional shear, so multiply by impact factor. Same thing, if I want to get a change in length under impact axial loading. Is equal to change in length under impact axial loading is equal to change in length of the same member under static axial loading multiplied by impact factor. Similarly, want to get the impact deflection. Deflection means it's going to be under bending. Then you have to take the static deflection multiplied by impact factor. So like that, what now? You can get any parameter. You want to get the impact stress, take the static stress multiply by impact factor. Impact deformation, static deformation multiply by impact factor. So you already know, so far you already completed what, how to find out the stress, strain, deformation, static loading. So once you know how to determine the stress, strain, deformation and static loading, then you want to get an impact loading, what do you have to do it now? That should be multiplied by impact factor. So students should be familiar only with impact factor. So one extra equation required. So now all the impact loading problems he can complete, because already in the strength of material, what you have studied now? What the aim of the strength of material is studied now? Derive the expression for stress, strain, deformation under different static loads. So you already know. First chapter pure axial loading. What the axial stress? P by A. Change in length PL by AE. Similarly, we want to get the impact axial stress. Therefore, static axial stress multiplied by impact factor. And if you want to get the change in length under impact axial loading, change in length under static axial loading, that PL by AE multiplied by impact factor. So like this, you can do it anything. So what should be the first step now? Assume the given impact load as a static load now. Assume the given, when you are solving the problems, assume the given impact load as a static load. Then next step is what now? Under the static load, find out the, write down the expression for stress, strain, deformation. Next, you have to calculate one extra parameter, the impact factor. Then impact stress equal to static stress multiplied by impact factor. Impact deformation equal to static deformation multiplied by impact factor. So only additionally we need a expression for the impact factor. Given impact load, should be assumed as corresponding static load. What is the meaning of corresponding now? Impact axial load means you have to take the static axial load. Impact bending, then you have to go for the what now? A simply support beam under impact bending. Then you take the what now? Simply support beam under static bending. corresponding static load. Next, determine deformation static deformation, that is what the change in length under static axial load, PL by AE, static axial load. Similarly, what now? Theta TL by GJ, then deflections. These are all static deformation. So the C2 value will change now. C2 value will change. For cantilever beam under point load, these constants you are going to study in the deflection of the beam chapter. That only I am going to give in the tabular form. Only you have to remember the C1 and C2. C1 is the constant for a slope and C2 is the constant for a deflection. So when a cantilever beam subject to a point load at the free end, what the constant? No, 3. When a simply supported beam subject to a point load at the midspan, 48. Same thing, if you want to get a slope, you have to take the what? A C1 should be there now. Next, by using some equations, by using strengthometrical equations. Next, impact factor. IF means impact factor. Should be calculated. So only this expression should be remembered now. Impact factor is equal to 1 plus square root of 1 plus 2h by delta static. 1 plus square root of 1 plus 2h by delta static. So only what the data is required now, h is required. H is the input data. H is the height from which the weight is allowed to fall. H is the height from which the impact load is falling now. Impact load is falling. So h is given as the input data. If the h is not given as input data, velocity is going to be given as input data. Then we are going to assume the what? A freely falling body. For a freely falling body, initial velocity is 0. Then v square equal to 2gh. Then h is equal to v square by 2g. Most of the question they are giving directly h. From which height that load is fall now. If h is not given, velocity is going to be given v square by 2g. V square by 2g. So this is valid what? For a freely falling body. Either velocity or h is given. And this is already calculated. This is already calculated. So this one expression should be remembered now. 1 plus square root of 1 plus 2h by delta static. Sir, how we got it? That also I am going to explain. Now, so what the minimum value of impact factor? Minimum value of impact factor is going to be 2. If h is 0, this value is 2. If h is non-zero, this is greater than 2. So impact factor is minimum is 2. Means what the meaning now? all the impact values are minimum 2 times the static values. If h is going to be increased, then still impact factor will increase. So the minimum impact values are 2 times the corresponding static value. Minimum 2 times will be there, but actual value is going to be depend upon the h value now. Then determination of impact deformation. Delta I means impact. Same thing, if you want to find out the impact stress, first you have to calculate the static stress. Determination of static stress. By using corresponding from equations. Sigma static, these equations you have studied, or the axial stress P by A or M by Z. The maximum bending stress and maximum torsional shear stress. Then impact stress. Sigma static multiplied by impact factor. Only this equation should be remembered it now. But what is the meaning of h tends to 0? H is not 0 when h is very, very small. When h is very, very small, the impact factor is almost equal to 2. Impact factor is equal to 2. When h is 0, h is not 0, h tends to 0 means what? When h is very, very small, the impact load is known as suddenly applied load. That is SAL, suddenly applied load, SAL. Hence, This short form SAL, but what the other name you can call it? What the other name now? Instantaneous load. Instantaneous load. Instantaneous load. Suddenly applied load or instantaneous load. So directly can write down as what? 2 times the static stress and static deformation. Some of the state service examination directly there, when a load is applied as static load, stress 100 megapascals. When the same load is suddenly applied, what the stress now? Directly 200. So in suddenly applied load, directly take the values what? 2 times. So this impact factor calculation required in case of impact loading. But sometimes whenever H is given, that is going to be taken as what now? Whenever what now? H is given, that is what? Nothing but an impact load. So then you have to calculate this now. Therefore, this impact factor calculations are required when H is given or when velocity is given. But in suddenly applied load or instantaneous load, directly you can take the 2 times you are going to take it now. Now with this one, now you can do all the calculations, you can do it now. All the calculation you can do it now. Only I am explaining the impact axial load. A bar is what now? Fixed at the top and bottom end of what now? A flange or a collar is attached. Flange or a collar is attached. A weight of W is falling from height of H. So weight of W is falling from height of H. So for this bar, this will become as what? For this bar, this W will become as what? Impact axial load. This is what this load is acting along the longitude axis of this bar. So for this bar, this will become as what? Impact axial load. The W will become as what? Axial load, but it's falling from height, impact axial load. So once this weight falls onto this one, what happens now? Once this weight falls onto this one, what happens now? Here reaction upward will be there now. Reaction in the upward is going to be there now. Then the bar, this end is fixed now. This bar is going to be elongated. Bar is elongated. Then automatically what? The flange is going to be displaced. The flange is going to be displaced. So the displacement of the flange is equal to elongation of the bar. Displacement of the flange is equal to elongation of the bar. Once this weight falls onto this now, now this W is acting downward. Once this weight falls on this, and what happens? This W is acting downward. Reaction is upward. Then the bar is going to be subjected to axial load. This weight is acting with respect to bar. What happens? This W is acting downward direction. Axial tensile load. And here reaction upward. Then automatically the bar is going to be elongated. But the top end is fixed. So the total elongation will be on the downward will be there now. So bar will be elongated. When the bar is elongated, automatically what now? Flange is going to be displaced. Flange is displaced. So this dotted one is representing the what now? Final, that is the deformed shape of the there is no change in the dimension. The flange is what? Simply displaced now. Bar is elongated. So this you are calling as what now? Impact elongation. Elongation of the bar, but there is no change in the dimension of the flange. Therefore, it is called as what now? Displacement of the flange. In place of the change in length of the bar, they will call it as what now? What is the displacement of the flange? Nothing but the change in length of the bar. Delta I means impact elongation. I means impact. Now, what should be the actual principle here now? Work done by the load. What the work done by this load now? What the work done by this load now? W into H plus delta I. Here yesterday I mentioned is a suddenly applied load, impact load. We cannot take the average work done. So what the work done by this now? Everybody is going to take the W into H. W into H plus delta. So what the work done by this now? W into H plus delta. They will forget about this now. They will take directly W into H equated to energy absorption now. So what should be the actual principle now? Work done by the load. Should be equated to, so this is the external work done. Then the bar should have the ability to absorb this energy. This work done nothing but external energy. So if the bar should not fail, the bar should have the ability to absorb, therefore that should be equated to strain energy. But if I am going to remove this weight, once again it will come back to its original position, means undergoing elastic or plastic, no, elastic. So which strain energy you have to consider? Resilience of the bar should be considered, no, resilience of the bar under axial load. So you have to equate it to the strain energy of bar. So what the work done by this load now? W into H plus delta I. What the strain energy equation written now? What the strain energy equation written now? Under axial loading, pure axial loading, what the equation written now? P square L by 2AE. And what the other equation written now? Sigma A square upon 2E into volume. Just now pure axial load, what this bar is under pure axial loading now, but pure axial impact load. So pure axial load, what the equation? P square L by 2AE. P square L by 2AE. But in terms of the axial stress, what I write now? Sigma A whole square upon 2E into volume. But we have to take the which stress now? Either impact load, then you have to take the impact stress. Sigma I whole square 2E into volume. So what this term is representing now? Resilience of the bar. Resilience of the prismatic bar under impact axial loading. Impact axial loading. Now you can simplify, that's all now. You will get an equation. If you want to get the equation for sigma, if you want to get the expression for sigma, then this delta should be replaced in terms of the sigma. What the change in length equation? PL by AE or sigma L by E. I want to get the equation for sigma. Then you replace this in terms of sigma. In terms of sigma is what now? Sigma I L into upon E. Otherwise, if you want to get the delta I equation, if you want to get the expression for delta I, then write down the sigma I in terms of delta. So this should be that's why starting I not discuss. For this one you need a strain energy. Yesterday I discussed now. Now simplify it now. Now we are going to get an equation, quadratic equation. Yesterday already I studied strain energy. They always about now second order function. Strain energy is proportional to sigma square, proportional to delta square, proportional to p square. So the second order. That's why you are getting a sigma square. Now we are going to get a quadratic equation. Write down the roots of a quadratic equation. What are the roots of a quadratic equation? Minus b plus r minus square root of b square minus 4ac by 2a. So what this equation you are going to get it now? Equated to 0. So this term you are calling as ax square plus bx plus c. What the x means? Sigma I. What the a value now? This is a value. This is b. This is c. Now write down the roots. What the x? Sigma I equal to minus b. What the b value now? Minus of sigma, sorry, b value is what? A minus of WL by E. Minus b plus r minus square root of b square minus 4ac. Simplify it, you will get that impact stress equation now. But you take the plus root or minus root. You take the plus root or minus root. Always here enters the maximum stress. If you want to get a maximum stress, you have to go for the plus root. Always you are interested in the maximum stress. Minus b. So it will become as what now? WL by E. B is equal to minus WL by E plus R minus B square minus will become as a whole square plus minus of 4AC. It will become as a 4. A value how much is now? AL by 2E. What the C value now? Minus WH. You have to put them with a minus sign. We are going to take the plus root. Minus B plus R. Sorry, you have not taken minus. But already this is what the minus is there. Minus will become the plus. Minus B plus R minus square root of B square minus 4AC to A. What the A value now? So simplify, you are going to get it. The actual equation simplified, you are going to get it now. Now this W by A, this W by A is nothing but about the axial stress, that is the static stress. Static stress. And this total you are calling as about now impact factor. Impact factor. And if I bring this A into denominator, it is the delta static. If I bring the A into denominator, it is the delta static. So what you are writing now? Impact axial stress, impact stress is equal to sigma static multiply by impact factor. So this is the equation I am using now. This one is better or this one is better? These equations are better or this is better? In all the textbook they will write down this only. This is valid only under impact axial loading. Impact bending is not valid now. But this is valid what now? This is valid under impact axial loading, impact bending. But if you go for a impact bending, this will become as what now? M by Z. If you go for same thing, if you do it in impact bending, this will become as what? This equation what now? Impact stress or impact stress under axial load. This is what now? Impact stress under which type of load you have taken? Axial loading. IAL means what? Impact stress under axial load. So this equation valid only under impact axial loading. Similarly, if you want to get an impact bending, you have to remember one more equation. Impact bending, what should I write now? M by Z, then 1 plus 2H WLE, WL cube and C2EI, you are going to get it now. So that all the equation difficult to remember it. All the equations are difficult to remember it. But this is valid for what? Any loading. Impact loading, impact axial loading or impact bending. Any case you can use it now. You know already. Static load means what I have to do. The axial load means P by A. Bending means what should I write? The M by Z. So this I have written now. Therefore this is valid for any loading. This is valid only under impact axial loading. But on all the students and all the textbook they are doing this only. They will explain this case only. They will explain this case only. This is studied in the chapter number 1. Because in the chapter number 1 they are doing the axial loading. They will explain, they will do this only. But if a question is given, one of the engineering service paper, they are given a bending is given. Most of students they left it now. But who knows this one directly can do it now. So this is valid for any impact loading. Axial load means P by A. Bending means what now? M by Z. And what the delta static under axial loading? PL by AE. Bending case WL3 by C2 into EI. WL3 by C2 into EI. So those equation already studied in the strength of material studied now. But these are all what now? If you most of them are going to try to remember it now. If you try to, this is lengthy, and even if you are going to by heart it, that is valid only under axial loading. But bending case is not valid. For bending means once again you have to remember now, m by z, 1 plus square root of 1 plus 2h in plus of AE, what you are going to get now? C2 into EI, WL cube you are going to, they're all difficult to remember it, and even if you are remembered, but difficult to recollect in the exam. Timing you can remember because you are doing the only strength of material. But in the February 2nd week of 2023, where you are appearing for 40 subjects of 4-year syllabus now. So if you are going to by heart each and every equation, they're all difficult to recollect it. So this is a better way. That's why this method I am going to use it now. Now, how many ways this impact stress can be decreased now? Yesterday what you have studied now? Always chance of failure is what? What the minimum value of the impact stress? The minimum 2 times of the static stress. Minimum 2 times of the static stress. Suppose impact factor value is what? A 4. If this bar is pulled with the axial load of W, stress induced is some 20 megapascal, but the same weight is falling from a height. Then suppose the impact factor is 4, then what the stress you are getting? 80 megapascal you are going to get it now. So always the impact stress is more than the impact stress. Impact deformations are more than static values. Therefore chance of failure are more. But what the design engineer has to do it now? He has to design in such a way that he cannot control the load. He cannot control the type of load. He cannot control the magnitude of the load. Only he can control the what? The shape, material, dimension. Now how to reduce this now? How many ways you can reduce this now? Load cannot be controlled. First material is selected. You have to select a material with a lower Young's modulus or higher Young's modulus, lower Young's modulus. Then you have to provide the more length or less length. I want to reduce this now. Chance of failure should be less means what? Impact stress should be less. If this should be decreased means what now? I have to select a material with lower Young's modulus. Once I select a material, suppose I have taken a mild steel. Suppose I have taken mild steel for a given material, Young's modulus fixed. Then still I want to further decrease. Now I have to provide a dimension. I have to provide the more length or less length. More length. That only yesterday I discussed now. Bolt subjected to impact loading is made as a longer. Yesterday I explained with the strain energy concept. Now I am proving here now. If L increases, automatically impact factor decreases. When impact factor decreases, impact stress decreases. Next, area. Shall I provide more area or less area? Here, inversely proportional. Inversely proportional. Therefore, if you want to decrease this one, you have to provide more area. But sir, it's proportional. But this is what? The square root of A. Sigma is what now? So want to decrease this now. Which one is the better now? Increasing area, decreasing area. Suppose the area becomes double. Areas become double. Stress is what now? Become half. But if I am increasing the area, if I increase the area, this will not be what the same now. So always which one is better now? Increasing the area is better now. Increasing the area. So if you increase the area, what now? This will increase, but this is proportional to A. Proportional root to A. So which is the better now? Increasing area, decreasing area, increasing. So area should be increased, length should be increased. Means indirectly what should be increased now? Volume should be increased. So impact stress under axial loading. Impact stress under axial loading can be decreased by selecting a material with a lower Young's modulus. What is the meaning of this now? Young's modulus cannot be decreased. For a given material, Young's modulus fixed. What is the meaning of this now? selecting a material with a lower Young's modulus. Somebody, sir, how can you decrease that? What the meaning of this now? Selecting a material with a lower Young's modulus, providing more length, providing more area. So indirectly these two are called as what? A volume. And because this one automatically strain energy also increased now. Yesterday what you have studied now, proof resilience can be increased. Proof resilience can be increased. How many ways you have studied now? Selecting a material with a higher elastic limit, lower Young's modulus, and providing more volume. So either you can explain with the equation, otherwise what now? What the other way to explain now? With the strain, because of all this thing, what happens now? Strain energy will increase. When energy absorption increases, when the strain energy increases, chance of failure are less. Yesterday I studied the proof resilience can be increased. What the proof resilience here written yesterday now? Stress at elastic limit whole square by 2E into volume. So if the proof resilience should be increased, mean what you have studied now? Selecting a material with a higher higher elastic limit, lower Young's modulus, and more volume. Same thing. But in the interviews, everybody is going to explain with these equations. But interviews will not what now? If you are going to explain the answer with the equations, they will not be satisfied with your answer. Why? How do you and I know whether you are explaining your answer with the equation? I don't know. You might have written incorrect answer, incorrect expression. Most of them are going to try to explain the what now? Answers with the equation. Why you have selected a lower Young's modulus? Why you have to select a material with a lower Young's modulus? Why you have to provide the more length and more area? Everybody is going to explain with this, but they will not be happy. Interview committee will not be happy. Because you might have made a mistake in the equation. They will not remember that equation. So you have to explain with the concept. What you have to do it now? What is the explanation now? Sir, by selecting a material with a lower Young's modulus, provide the more volume, strain energy will increase. When the energy absorption increases, chance of failure are going to be less. That is the better way to explain now. Because they will not remember the equation. They might have completed the BTech or MTech 30-40 years back now. Whoever is sitting in the interview panel, especially engineering service UPS committee and civil service committee UPS committee, they are all what now? Almost retired or yet to be retired now. So they might have completed their BTech 30-40 years back now. So they will not remember all this thing now, but they know the concept, they know it now. So try to explain your answers with a concept. Same thing if you go for a bending. If you go for a bending, what change you have to make it now? Selecting a material with a lower Young's modulus, more length and more moment of inertia. This is what valid under axial loading. But in case of bending, what change you have to make it now? More moment of inertia. More moment of inertia should be there now. More moment of inertia. So this should be replaced under bending. This should be replaced by moment of inertia. In the place of strategy, there will be a delta AC. What is the delta AC, my dear friend? What is the delta SE you are written? Who is this now? Manas. What is the delta SE? What is the delta SE, my dear friend? Sir, in place of SE, you have tried down the delta SE. What is the delta SE? So this is a actual one now. But now when you are solving the problem, what should be the first step you have to do it now? When you are solving a problem, what should be the first step now? This is actual method. This is actual method now. But when you are solving the problem, what the first step? This is a problem now. What should be the first step you have to do it now? This load should be assumed as a what now? Impact load. The impact load should be assumed as a static load. This is the first step. The given impact load should be assumed as a corresponding static load, is the axial load. So this comes under what? A pure axial static load. Pure static, pure axial load. But this is about the impact axial load. This is about the static axial. This only is still the first chapter now. So for this one, you know the equations. What the delta static. Next one. Impact factor. Then delta impact. That's all. Then if you ask the stress, if we ask the stress, what should I have done now? W by A, axial stress. This is what a static stress, static axial stress. Then impact stress. That's all. Objective examination, they are asking either impact elongation or impact stress is going to be asked now. Then you can do it now. So numericals are given. You can complete this now. I am giving you some numericals here. So now you can do the calculations now. Why you have to take this change in strain energy, my dear friend? Who mentioned the change in strain energy? Strain energy is what the energy absorbed. Where is the change in strain energy? Don't use the word everything you explain and you are telling the change in strain energy. Who mentioned the change in strain energy now? Are you attending the class or not? What the strain energy you mentioned? Energy absorbed, that's all. And you are mentioning the change in strain energy. Where you have studied the change in strain energy? What the strain energy now? Energy absorbed. What the meaning of change in strain energy? Have you any change in strain energy concept? What the strain energy means? Energy absorbed, that's all. Where is the question of change in strain energy? Please don't try to use the lower standard concept. Never have you attended so many strain energy. I mentioned clearly what now the work done should be equal to energy absorbed. Where the question of change in strain energy absorbed now. That only the problem will be there now. We are going to the low standard concept. And after attending the class also, we are going to the low standard whatever you have studied now. And my friend Mr. Manas is telling, sir, you have to equate the work done to the change in strain energy. I don't know what is the change in strain energy. Do you know the concept of strain energy or not? So much of time concept you have studied and you are telling you the change in strain energy. What is the change in strain energy, my dear friend? This is what a cantilever beam is. Which type of load? A constant point load, but is falling from a height of h. What is the example for this now? What is the example for this now? IJAR test. When you have studied the impact test, two type of test you have studied now. What is the IJAR and Charpy test? In IJAR test, specimen is supported with a cantilever beam, fixed at one and subjected to impact bending. Charpy test, specimen is supported as a simply supported beam. This is what now? When you are doing the IJAR test, the specimen is supported like this, and you are lifting the hammer, and you are releasing like this now. So how this load is acting now? Constant point load. But it is what now? Striking with a velocity. Therefore it is what now? It is what now? Impact bending. So this is what now? The specimen in case of IJAR test is taken as about a cantilever beam subjected to impact concentrated point load. Impact concentrated point load. The same example now. There you are trying with a velocity. If you know the velocity, you can find out the h, you can find out now. Same thing in Charpy test. What you are doing now? Charpy test. The specimen is supported. My two hands are nothing but a simple supports, just like a roller support, simple support. And the hammer you are lifting now. You are releasing. Then it will become as what now? A simply support beam subjected to a constant point load at mid span. A constant point load at mid span. So what should be the question? What the method you have to use it now? Once a problem is given, what the first step now? Same. This is what now? Is the impact bending. This is static bending. That's all same now. What the next question now? Next step is what now? For this one, what the deflection you studied yesterday? WL3 by 3 EI. What the C2 value now? 3. 3. So for deflection calculation is sufficient. Similarly, if you ask the stress, what is required now? Bending stress means you need a bendiment. What the maximum bendiment? What the bendiment diagram here now? You have studied what the bendiment diagram here. Bendiment is 0 here. Bendiment is maximum now. What the shear force now? W. What the bendiment? W into X. Here what the reactions now? W Directly what the bendment here now? Whenever you want to get a bendment at extremement, there should be a bending couple. There is no bending couple, means bendment is 0. At B, you will get only shear force. At B only shear force. At A, both shear force and bendment is there. So what the BMD? Here bendment is 0. Directly what now? Sir, how do you know bendment? Whenever you want to get a bendment at the extremement, we need a bending couple. There is no bending couple. So directly bendment is 0. Here directly this couple is what? A bending couple. Directly this will become as a bendment. Is a negative or positive? No, negative. Left hand side anti-clockwise negative. Clockwise a positive. Then how to join it now? Here to here how many ways you can join it? Linear or parabolic now? What is the shear force equation? Shear force a constant. What is the shear force here now? W. When shear force constant, bendment is going to be very linear. Bendment variation 1 order higher than shear force. Want to write down the equation? You can write down now. You can also see what the shear force here now? W. Here also shear force W at A and B. And what you have studied? Between two axial load is a constant. Similarly, between two constant point load, shear force a constant. Between two twisting coupled twistment is a constant. Here one constant point load, one constant. Therefore, directly shear force a constant. So, what the SFD? Is a positive shear force or negative? Positive. It is also positive. SFD is a positive rectangle and BMD is a what? A negative triangle. What the SFD you are going to get it now? Every constant point load is not a shear force, but constant point load extremement is a constant point extremement. What the shear force directly? W. Plus W or minus W. Left hand side upward is a positive. Right hand side downward is a positive. And here also positive. Then automatically what? You will get a rectangle. Now the shear force a constant. Bendment should be varied linearly, and this is the maximum bendment now. So tomorrow when you are going to do the SFD BMD, I am not going to explain all this thing, all the basics you have studied now. All the basics you have studied, how to write down this now. Section method, already you have taken W, shear force is W plus W. Bendment is what now? W into X. Though whoever is attending tomorrow lecture SFD BMD, please try to refer shear force bendment definitions, sign conventions, then you have done some calculation. Otherwise, we will not follow this topic now. The things which are discussed, they are not going to be repeated. The things which are discussed, types of supports you have discussed now, they are not going to be repeated. And cantilever beam reactions you have studied now. So directly I will go for the problems only. And you have studied bendment variation 1 order higher than shear force. If you are not thorough with this now, then tomorrow it is going to be very difficult to understand. And if your SFD BMD are not thorough, then deflections are going to be difficult now. Deflection of the beam is also difficult now. So what is the first step now? Delta static. Next, impact factor. Next, impact deflection. Next, if you add the stress, so first you have to find out the static bending stress. For the bending stress equation, M by Z, M max upon Z. Bending stress equation you have studied now. So what the maximum bendment? WL. Maximum bendment is WL. Suppose by chance a rectangular cross section is given. If a rectangular cross section is given, what the section modulus? The vertical bending which is the neutral axis HCA. So what the section modulus now? BD square by 6. And what the moment of inertia here now? For rectangular cross section, what the moment of inertia? BD cube by 12. Four will be there. Double BD cube by 12. So it will become 4WL cube by E BD cube. So you can calculate this now. And this will be 6WL upon BD square. Then you can calculate the impact stress. So to solve this question, what is required now? We need deflection of the beam concept is required. Then impact load for impact factor concept is required. Bending stress equation required, and bending concept is required. So for this one, we need the BMD, SFD BMD concept is required. That is chapter number 3. Next, this is studied in what? A bending stress chapter number 5. And this is studied in what now? Deflection of the beam chapter number 4. Then impact. So total 4 chapter concepts are required now. SFD, this is studied in SFD BMD. Already what explained now. When you are studying the equivalent loads now. Clearly given a generalized now. Already discussed the bendiment, shear force, twistment, all now. So SFD bendiment calculations are required. Next, there is a chapter number 2. Next, deflection of the beam. Only this I have not discussed now. This has to be studied, but directly about now. The C2 value are given. This only I have not discussed now. You can ask some doubts, sir, how you got it. That I am going to discuss the deflection of the beam chapter now. Remaining all you have studied now. Then bending stress equation required. M by Z. Section modulus neutral axis. Is a vertical bending which is the neutral axis now, HCA. How to write down the moment of inertia. How to write down the section modulus you have studied now. Then we need the concept of impact loading. So many concepts are required here now. But in objective, sir, is it possible for any one question may ask now? They will ask only impact deflection or impact stress will be asked now. So beam to beam, what change you are going to get it now? Suppose a simply supported beam is given. That is a Charpy test. Charpy test is what now? Simply support beam subjected to point load at the midspan. Then the constant is 48. In plus of 3, you have to go for 48. Then maximum bendiment equation will change now. So once again I am giving the numerical data. This you can complete it now. Always for beam, depth should be more or width should be more. Depth should be more. Thick and narrow rectangular cross section is better now. I can do all these calculations now. So I'm not spending the time on the calculation portion. Okay, good. Whatever you are given example is good. Anurag. Sir, this is also same example of jumping platform at swimming pool. Good. Used to jump from a height. You are good. Absolutely correct. The same example. Where you are going to come across this, like a swimming pool, diving boards are going to be there now. When you are diving into a swimming pool, the same thing now. The same example you are going to get it now. This is example for Charpy test. It is about a simply support beam, simple support, two hinge supports subjected to impact constant point load at mid span. This total distance span. This impact constant point load. So once again the same concept should be used it now. Entire year SFD, BMD, these questions here. This is about now static constant point load. Static constant point load. Once again, not a pure bending. Pure bending means always when you will get it now. Pure bending is possible when you apply the two bending couple at the extreme end. So these are all the example of simple bending. Simple bending means what you have studied now. Shear force is non-zero, bendment is going to be varies. Always what when a beam is subjected to constant point load or TSLs. Whenever a beams are loaded by constant point loads or TSLs, they are under simple bending, not pure bending. Total beam never will be a pure bending. Under transverse shear loads, total beam never will be a pure bending. But part of a beam may be pure bending. Part of a beam means portion of beam may be a pure bending. Total beam will be never under pure bending. Pure bending means what? Bendment is constant, shear force 0. So that is possible only if the total beam should be a pure bending. So many times I discussed. Total beam a pure bending means you have to apply the two bending couple at the extreme end. But beams are always loaded by transverse shear loads. Under transverse shear load, total beam never will be a pure bending. But a part of a beam may be pure bending. A portion of the beam over which the bendment is constant, shear force 0. But total beam never will be pure bending. That's why most of the beams are under simple bending. Simple bending means shear force non-zero, bendment is varies. So what the difference between pure bending and simple bending? Pure bending means bendment is constant, shear force 0. Simple bending, shear force is non-zero, bendment is varies. Shear force is non-zero, bendment is varies. And pure bending, every surface will bend in the form of a circular arc. Every surface bend in the form of a circular arc when you are studying the sagging and hogging now. But simple bending, they will what now? beam will be bent in the form of a non-circular arc, parabolic shape you are getting. It is not a circular parabola shape you are getting. So beam will bend in the form of a circular arc, only pure bending. But in case of simple bending, the beam will bend in the form of a non-circular parabolic shape. You are going to get it now. Parabolic shape. So here, what the shape you are going to get it now? What the shape now? Is a simple bending or pure bending? Simple bending. Here, what the reaction is? Symmetric loading now. It is a symmetric loading. What are the reactions now? What you have studied? Simple support, there is no moment reaction. Simple support, there is no moment reaction. Simple support is a hinge support. Hinge support, how many reactions are there? Horizontal and vertical. But horizontal reaction 0 because there is no axial load. Only you are getting a vertical reaction. And it is symmetric loading. This load is acting exactly at the middle now. Symmetric. What is the meaning of symmetric now? With respect to both the supports acting exactly at the same distance. Symmetric loading. Under symmetric loading, reactions are equal and half of the total load. Reactions are equal and half of the total load. What is the total load? No, W. So W by 2, W by 2. And reaction will be opposite the net load. Since net load is downward, therefore reaction will be upward now. Otherwise, how to find out now? Using sigma V and sigma statically determinate beam. How many unknowns now? RA and RC. Two unknowns, two equation. What are the two equation now? Sigma V is equal to 0 and sigma M is equal to 0. But that method is optional. That is compulsory. It is here is optional because of symmetric loading. And what the bending couples are 0. Because no moment reaction. Moment reaction is possible only at the fixed support now. Now, can you draw the SFD? What you have studied? SFD similar to ALD. SFD similar to ALD. I am starting from the left side. I am starting from the left side. Use the left hand side sign convention for shear force. What the left hand side shear force sign convention? Upward is a positive. What is the meaning of this now? So the shear force is going to be what? A positive. Positive. What is the meaning of this now? When I am going from left to right, all the upward load should be positive, downward load should be negative. Either positive, negative, positive. That only mention ALD, SFDs are what now? SFD are drawn similar to ALD when concentrated loads are there. TMD is also similar to ALD. That's why I mentioned what those who are thorough with the ALDs. For them, SFD and TMD are same. So this is a positive, negative, positive when I am going from left to right. But those who are starting from the right side, right hand side, which sign convention? Downward is a positive, upward is a negative. So those who are starting from the right side, this should be taken as a negative. This should be taken as a negative, positive and negative should be considered now. Tomorrow I am going to do all these steps only. Tomorrow I am not going to write down the equation. All the questions I am going to complete with directly from the diagrams. I am not going to write down the equation. Already you have studied how to write down the shear force and bendment equation taking as sections. That I am not doing. Directly I am going to draw like this only. So what is the next step now? When you are drawing the ALD, what you have done it now? Drawn a parallel line to the longitude axis until next axial load. Now draw a parallel line to the longitude axis until next constant point load. Where is the next constant point load? Here also same concept can be used it now. Left hand side upward is positive. SFD can be drawn similar to ALD, but I have not used by now. Because between two axial load are constant. Similarly, between two constant point load, shear force a constant. So here it is a constant. Next, since you have taken upward positive, downward is negative. So plus W by 2 minus W. Next, draw a parallel line. Next, upward is a positive, minus W by 2 plus W by 2, 0. What you have studied, SFD should be closed at both the ends. When SFD is closed at both the ends, means what? The sum of the vertical force 0. And how to cross check this SFD is correct or incorrect now? Number of vertical lines are equal to number of constant point loads. How many constant point loads here now? 1, 2, 3. 3 vertical lines. W by 2, W and W by 2. Now this is a constant point load or shear force? Constant point load. What the shear force now? Plus or minus W by 2. Whenever a constant point load applied at junction, 2 shear force are going to be there now. When you use the section method, what you have done it now? First you have calculated for AB, next you have calculated BC, then you have taken a larger value. So directly what the shear force here now? When this is shear force or constant point load? Constant point load. But when B belongs to AB, it is acting as a plus W by 2. When B belongs to BC, it is acting as a shear force of minus W by 2. Same thing here also you can see it now. Number of vertical line SFD are equal to number of constant point load. How many constant point load? 2. 2 vertical lines. How many vertical lines? BMD. Only one vertical line. Number of vertical line BMD are equal to number of bending couples. How many bending couples are there? Now 1. All these conclusions I have made it now. Number of vertical lines ALD are equal to number of applied axial load. Number of vertical line SFD are equal to number of constant point loads. Number of vertical line BMD are equal to number of concentrated moments are a bending couples, and height of the vertical line in SFD equal to magnitude of the constant point load. Height of the vertical line ALD equal to magnitude of the applied axial load. Height of the vertical line BMD equal to magnitude of the bending couple. Everybody is going to tell what? Sir, a beam is subjected to shear force sir at B. When I am doing the offline batches now, they will come to the word now. Sir, I am having a doubt, sir. Can you explain your doubt? Means, sir, beam is subjected to shear force at B, sir. So many times I am going to repeat, but they are going to mention the shear force. Sir, this is shear force, sir. Then automatically this is shear force. Constant point load will become as a shear force only extreme end. Now you can also check it now. How many shear force you are getting? 2. It is not a shear force, a constant point. So many times I mentioned, every constant point load is not a shear force. But constant point load extreme end will become as a shear force. But when a constant point load applied at junction, 2 shear force is going to be there now. Now what the bendment here? Now 0. Extreme end what? Now to get a bendment what is required? Now bending couple is required. But there is no bending couple. Therefore directly bendment is 0. That only I mentioned now. Every simple support bendment is not 0. But moment reaction is 0. But it's simply supported and what you have mentioned now. Both shear force and bendment are sorry. Moment reaction bendment both are 0. Moment reaction and moment reaction 0. Therefore bendment is 0. Clearly mentioned at extreme end. To get a bendment, we need a bending couple. There is no bending couple. Bendment is 0. Here also 0. You can check in at the extreme end, but there is a couple is there. That directly that is a bendment. Here there is no couple. Directly bendment is 0. So here bendment is 0. Here bendment is 0. Now here how many times you have to find out the bendment now? How many times I have to find out the bendment now? If a couple is there, you have to calculate the what? 2 times the bendment now. But here how many bendments will be there? Only 1. When a constant point load applied at junction 2 shear force, then shear force should be calculated 2 times. When a bending couple is applied at junction, you have to calculate the bendment 2 times. But there is no bending couple. Therefore here you are going to get the 2 shear force and 1 bendment only. 2 shear force and 1 bendment. 2 shear force, but bendment is 1 only. So what is the bendment definition? Algebraic sum of the couples and moments. Shall I take the left side or right side now? Left side only 1 moment. So what is the bendment here now? Algebraic sum of the couples and the moments either on the left side or on the right side. I am taking the left hand side. There is no couple. What is the moment now? W by 2 into L by 2. W by 2 into L by 2. Left hand side clockwise a positive. What is the bendment definition? Algebraic sum of the couples and moments. Left side there is no couple, only moment. What is the moment value? Now force into perpendicular distance. W by 2 into L by 2. WL by 4. Clockwise a positive. So I want to take the right side. You can check it now. Right side also what now? W by 2 into L by 2. Right hand side anti-clockwise positive. Left hand side clockwise positive. Right hand side anti-clockwise positive. Most of students what when I am going to discuss the SFD BMD, I have already completed the sign convention almost 5-6 days back now. Maybe after almost 1 week back I completed, but still they are not with the sign convention. And tomorrow when I am drawing the SFD BMD, sir, how it is the positive, sir, how it is the negative. They are going to wake up only when the problems are there. Till that time, they are going to sleep. Suddenly they wake up when the problems are there. But if there is no problems, they are going to sleep in the class now. And they will not refer the notes now. Even if the lecture is going on now. I am telling what this type of only failure category. My statements are not with respect to any of you. Don't feel it what now. Sir is criticizing me. My statement is not with respect to any of you. If any of you, my statement is by chance related to you, don't feel it what sir is criticizing you now. I am a best person. I am the well-wisher of all of you. Try to change. Change. First day I have given the power of change I have given now. Here it is what now? Sir, here shear force positive, sir. Here negative. How it is negative, sir? Is also upward. It is also upward. When both are upward, it should be a positive, sir. But this year taken positive, this year taken negative. Both are positive when you are going for sigma v equal to 0. Sigma v equal to 0, both are positive. But shear force, what you have studied now? Convention already given. Left hand side upward is positive, right hand side downward is positive. But right hand side downward is positive means upward is a negative, that's all. So this is what the W by 2. Sir, bendment is clockwise positive, sir. Anti-clockwise negative, sir. This is clockwise positive. This is anti-clockwise negative, sir. Left hand side clockwise positive, right hand side anti-clockwise positive. Clockwise positive, negative is what now? When you are going for the sigma m equal to 0. So whether you take any one, you are going to same. Now here to here, how to join it now? I don't have the bendment equation. For the actual method, I have to write down the bendment equation. Then I have to see the varying linear or parabolic. But that is not required. Why now? Once you know the shear force, directly can decide the bendment. Why now? Bendment variation always one order higher than shear force. A to B shear force a constant. Bendment is what varies linear. Suppose the SFD the inclined line, BMD the parabola, SFD the parabola, BMD the cubic parabola. Clearly mentioned bendment variation one order higher than shear force. How do you know it? Take a section. What the shear force equation? W by 2. Shear force equation W by 2. What the bendment? W by 2 into X. Shear force is independent of X. Bendment is a function of X. This is all you have proved it now. So here to here, how to join it now? Linear. So this is the maximum bendment. Bendment diagram is positive. Positive means sagging. Bendment diagram is positive means sagging. Sagging means what? Top surface gets contraction. Bottom is elongation. Bendment diagram is positive means sagging. Is a beam, horizontal member. Bendment diagram is positive means top surface gets contracted. Bottom surface elongated. But by chance, if a couple is there, what I have to do it now? If one constant moment or a bending couple is there, then you have to calculate the bend moment 2 times. Clearly mention, when a constant point load applied at junction to shear force, then shear force should be calculated 2 times. If a bending couple is applied, two bending moments will be there at the junction. Then you have to calculate the bend moment 2 times. That only yesterday, neglecting and considering that all the calculation you have done it now. But I'm not doing directly, I'm drawing the diagram based upon the conclusions now. So every time I'm not going for the equations. The equations are only to decide the what now. Is it a constant or varying now? But now tomorrow I'm going to do all this method only. I'm not going to write down the equation that already I studied now. That's all. Now, is it a simple bending or pure bending? Simple bending. Pure bending means bend moment is a constant, bend moment is varying. And shear force not the simple bending. Then it will not bend in the form of a circular arc. It will bend in the form of a parabola. So the beam will bend like this now. And this is the maximum deflection. This equation you are going to study. It is not a parabola. It is not a circular arc. Circular arc you will get only under pure bending. Circular arc you will get only under pure bending. That bend moment is constant and shear force 0. So this is the deflection. What this value now? WL3 by C2 into, but C2 value is what, a 48. Beam to beam only the C2 value will change now. So this will be only I not discuss the C1 and C2 values that I'm going to discuss in the deflection of the beam now. But try to remember it now. Anyway, you have to remember that C1, C2 values now. For cantilever beam point load, C2 is 3. Simply support beam point load at the midspan 48. Now you can do all the calculations now. For this question, SFD is required or BMD is required? BMD is required now. SFD is the option, but I drawn Y now. So how you have decided about now? Linear. Already mentioned, whenever what now? Bend moment variation always 1 order higher than shear force. So what the delta static now? WL3 upon 48 EI. Then impact factor. Only this equation will change. These two equations will change, that's all. 1 plus delta static impact factor. Then sigma static what the maximum bend moment? WL by 4. Maximum bend moment is WL by 4. Then impact stress. It's my pleasure, Mr. Swaraj Pandey. My lectures are always interrelated. Each and every lecture depend upon the previous lecture. They are not independent. Till now, no lecture is independent lecture is there now. Till last day also same thing is going to be there now. That's why I'm going to mention every student first day. It's a subject is completely interrelated. And the institute what now, Mr. our CMD sir, Mr. B Singh sir asked what now, so many times now. You split this subject just like Tom is divided Tom 1 and Tom 2. This also you can split into two parts, Psalm 1 and Psalm 2. You can give some portion to some of the simple topics, give it to some other faculty. You can take the mission, but I have not accepted for that now. Sir, this subject is completely interrelated. If I am going to split it, the students are not going to get benefited. I am ready to sacrifice my mission design for some batches now. For me, my satisfaction required so that students are going to be happy now. Otherwise, I am going to discuss some portion discussed by other teacher. So his presentation is different, my presentation different. And I am going to pronounce what so that I am going to interlink with respect to machine design. I am going to interlink now. Sir, somebody will ask, sir, can I draw the SFD like this always? SFD can be drawn similar to ALD only under concentrated loads. But when distributed loads, we cannot draw it now. SFD can be drawn similar to ALD only under concentrated loads. But when distributed loads are there, UDL and UL, we cannot draw it now. But torque diagram is always drawn similar to ALD. When twisting couples are there, always the torque diagrams are drawn similar to ALD. That's why I'm going to enter the loading concept first now. Loading diagrams. But some students will not focus on the ALD. And whatever the conclusions I made, they will not focus now. Then for them, once again, each and everything is a new point is going to be there now. Now, so like this, you can do any of the questions. This is what now? Example for what? The swimming pool platform. Other one is what now? IJAR test. This is about a Charpy test. Suppose I am getting this value. I am getting this value more than ultimate strength of the beam. If this value is greater than SUT, assume this is a mild steel beam. Mild steel ultimate strength is 400 megapascal. But I am getting more than 400 means what now? The beam will fracture. Beam will fracture. Beam will fracture. Then what the design engineer has to do it now? He has to decrease this now. How many ways he can decrease now? If you want to decrease this, which one I have to decrease now? Impact factor should be decreased. You want to decrease the impact factor, what I have to do it now? Delta static should be increased. Delta static should be increased. If I want to decrease this now, I have to decrease this impact factor. I have to decrease this now. And this also should be decreased now. How to decrease the impact factor? If the impact factor should be decreased, mean what I have to do it now? Delta static should be increased. If the delta static should be increased, mean what now? Length should be increased. And you have to select a material with a lower Young's modulus. You have to select a material, that only a risk. You have to select a material with a lower Young's modulus and you have to provide the more length. Sir, you have to decrease the moment of inertia. But if you decrease the moment of inertia, what happens now? This will increase now. What's the Z value now? Z is equal to I by how to decrease mean what now? Sir, you are mentioning length should be increased. Means you have to provide a more length. And you have to select a material with a lower Young's modulus. Sir, similarly, I have to select a lower moment of inertia. If you decrease this moment of inertia, delta static will increase. But this will increase. This will increase. If I am going to decrease, then automatically this will increase. That's why what I have to do it now. Here sigma is inversely proportional to I. Sigma is inversely proportional to I. But here impact factor is proportional to square root of I. If I am going to substitute this, I will come in the numerator just like in the previous case now. Axial stress, impact axial stress inversely proportional to A and proportional to square root of A. Same thing what now? Here impact stress under bending inversely proportional moment of inertia and proportional to square root of I. Proportional to square root of I. So which is more effective? Now increase the moment of inertia. That's why what I mentioned under impact bending. If you want to get an impact bending, if this should be decreased, mean what the option now? I have to select a material with a lower Young's modulus, more length and more moment of inertia. More moment of inertia. Only in case of axial loading, what in place of more area, here I have to write down the more moment of inertia. More moment of inertia. But what the other way can do it? What the drawback of this now? If I increase the length, it will occupy the more space, but that much of space is not available. And if I increase the moment of inertia, weight is also increased, length is also increased, and that much of space is not available now. Weight of the beam is increased. If I increase the length, if I increase the width and depth, moment of inertia should be increased, means once again width and depth should be increased. Then the weight will increase, and sometimes space a constraint is there and I don't have that much of space now. Then what the other alternative now? One alternative is what now? One alternative is selecting a material with a lower Young's modulus, providing more moment of inertia and more length. But this method is possible when now? During design or after design now? During design. After manufacturing, this beam is already constructed. After constructed, we cannot change the material, we cannot change the dimension. Whatever the method I have given, what now? Providing more length, more moment of inertia, selecting a material with a lower Young's modulus. This can be done during design stage, that is before manufacturing. But after manufacturing, we cannot change it now. After manufacturing, we cannot change it. We cannot change the dimension, we cannot change the material. Then what the other alternative now? After construction, I found that what now? After construction, beam is already constructed. Before applying the load, I cross-checked, the design engineer cross-checked it now. The beam is already what now? Constructed. So before it come into functionality, he has cross-checked it now. For the given condition, design engineer is given, is constructed. But before coming to the functionality, he has cross-checked whether this is safe or not by calculating this now. But this value I am getting more than SUT. Then means that beam should not be used in the application. But what I have to do it now? I cannot change the material, I cannot modify the dimensions now. What I have to do it now? What the other alternative now? I have to decrease this impact factor. I have to decrease this impact factor. How to decrease the impact factor? Increase the delta static. But without changing the dimension, without changing the material, how can you increase the delta static? What the other method now? Replace this rigid support by flexible supports. In place of the rigid support, use the flexible supports. Springs are provided. If spring is provided, what is my aim now? I have to decrease this what now? Impact stress. Means impact factor should be decreased. If impact factor should be decreased, means what? A delta static should be increased. But if I want to increase the delta static, I have to select I have to provide the more length, more moment of inertia and less Young's modulus. But that option is what? A possible before manufacturing. After manufacturing, we cannot change this method now. We cannot use this method now. So what the other alternative I have to do it now? This delta static is representing the what now? This is a beam deflection or supports deflection. Supports are rigid. The supports will not deflect now. Only beam will deflect it now. This is what a deflection of the beam or support now. These are the rigid. Supports will not deflect it now. Only beam will deflect it. Then what I have to do it now? Somehow I have to increase this now. I have to increase this now. Then what I have to do it now? Replace this rigid support by flexible supports. Flexible supports. If I am going to provide a flexible support, means springs. If I am going to replace by springs, what happens now? When this load falls on this one, what beam will deflect or spring will deflect? Both will deflect. Both will deflect. Then in that case, what change I have to make it here now? Either deflection of the beam. But if I am going to provide a spring, what change I have to make it now? Beam deflection plus spring deflection, both you have to take it. So automatically what now? delta static will increase. When the delta static increase, automatically impact factor decrease. When impact factor decrease, impact stress decreases now. So what the other way of decreasing the impact stress now? Providing the flexible support or rigid support. That's why what now? You can see your four-wheeler vehicles, all automobile chassis, they are supported by rigid or flexible shock absorbers are used now. All automobile chassis are subjected to impact bending. They are supported by flexible supports. Shock absorbers are used. But beams are supported by rigid support because beams are subjected to static bending. But automobile chassis is subjected to impact bending. That's why they are all supported by flexible supports. It's a very standard interview question now. Why buildings and structures you are in the rigid supports? Why automobiles you are in the using the flexible support like shock absorber? What the answer now? Beams are subjected to static bending, but automobiles are what? The chassis are subjected to impact bending. Then in that case, if the impact stress should be less, means what? More strain energy absorption. Now what the work done by this load now? W into H. So this much of energy has to be absorbed by only beam now. What the actual concept now? The work done by this load should be equated to strain energy of the beam. But the strain energy of the support 0. But if I am going to replace the springs, what happens now? The work done by the load is equated to what now? Strain energy of the beam plus strain energy of the spring. Once the energy absorption increase, automatically chance of failure is going to be decreased. So what the answer now? Instead of explaining with the equation, what the other way can do it now? Sir, if I am going to provide a what now? Because automobile charge subjected to impact bending, then work done by the impact loads are more. I need a more strain energy. If I am going to support by springs, then energy absorption will increase. Once the energy absorption increase, chance of failure are going to be decreased. Otherwise, you can explain with this now. Sir, by providing the flexible support, static deflection will increase. When delta static increase, impact factor decrease. When impact factor decreases, impact stress decreases. So for this one, what the alternative you have to do it now? So this is a better now. So which one is better now? First one is better or second one is better now? Here chance of failure are less. How many ways to explain now? What are the different ways to explain this? Why this is the best mean what now? Work done by the W should be equated to strain energy of beam plus strain energy of spring. So once the strain energy increase, chance of failure are less. So this is one way of explanation. What the other explanation now? This is one way of explanation. What the second explanation now? Delta static will increase. What the delta static means? Beam deflection plus spring deflection. When delta static increases, impact factor will decrease. When impact factor decreases, what the impact stress decreases. When impact stress decreases, chance of failure are going to be less. Sir, you mentioned providing more length, more Young's modulus, the lower Young's modulus, and more moment of inertia. That method can be used, adapted. That method is adapted during design. And but what is the drawback of that method now? What is the drawback of that method? Weight will increase. material increase, cost will increase. But this is what a better now. This is a better now. Weight of the beam is less, only springs are used now. But this is better in case of what? Impact bending. This is the principle for the your all automobiles now. So always under impact loading, flexible supports are better. Impact loading what now? Flexible supports are better now. So if this question is given, by chance this question is given, what change I have to make it now? Is the deflection of the beam. Then you have to find out the deflection of the spring. What the load coming out of the spring now? W by 2. What the load coming out of the spring now? W by 2. So the stiffness is given. If I go for the numerical problem, if this question is given, what change I have to make it now? Is the deflection of the beam plus by chance this question is given, you have to use this now. Deflection of the beam plus deflection of the spring. What the load coming on the spring now? W by 2. Stiffness is K, W by 2 K. So delta static will increase. When the delta static increase, impact factor decrease. When the impact factor decreases, then this will this you have to calculate. This you cannot directly tell because what now? This is increasing. Delta static is increasing and impact factor is decreasing. Mostly this is also going to be decreased. Check it now, but I'm not sure. This delta static is increasing, but impact factor is decreasing. So overall you have to check it. Mostly it should decrease now. Somebody will ask now. So delta static is increased, but impact factor is decreased. But this will decrease automatically now because this will decrease. So now this is the concept of the impact loading. Now you can do any of the questions. Either axial loading, mostly the questions are axial loading or bending. I have not done the numerical questions. Now you can directly have given a procedure. But most of the times 80% of the objective examination they are giving only axial loading, impact axial loading. That's why most of the teacher, most of the textbook they are discussing, because in the textbook they are giving impact axial loading. Teachers also discuss, some of the examiner also they will take the same question now. But there is a possibility of what now? Impact bending questions also going to be there now. But what the different? Only equation will change. Only equation will change. In place of PL by AE, I have to use the what now? WLQ by C2 EI. In place of the PL by AE, I have to use the WLQ by C2 into EI. The C2 values we are going to study now. For cantilever beam, point load at the free end 3. Simply support beam, point load at the mid span is 48. Next, axial stress P by A. Here M by Z. Then you know the maximum bending is required. Only equation will change. Equation will change. Procedure is same. So what the conclusion here now? Rigid supports are better or flexible supports are better? Mean what the answer now? Rigid supports are used under static loading. Flexible supports are used under impact loading, especially impact bending. Impact loading. Impact loading. Always flexible supports are better. So what is the use of the flexible support? Mean what the answer now? Since the work done by the impact load is more, then automatically strain energy will increase. Strain energy of the beam plus strain energy of the spring. Once the strain energy increases, then chance of failure are less. Or otherwise, by using the equation, since the delta static increases, impact factor decrease, impact stress decreases. So you have to answer what how many ways the impact stress can be what now. Chance of failure can be decreased means you can explain the two ways. One is what now? Selecting a material with lower Young's modulus, providing more length and more moment of inertia, axial loading more area. But this method is adapted during the design. After manufacturing or construction, this method is not possible. And what the one drawback of this method now? The weight is going to be increased, cost will increase. So what is the other option? What the other option? By providing a flexible support. By providing a flexible support, energy absorption will increase. Or delta static increase, impact factor decrease. When impact factor decrease, impact stress is going to be decreased. Still what the bend, sir, somebody will ask now, sir, whether Bendman diagram will remain same. You can draw the free body diagram, what happens now? Now which one is supporting now? Springs are supporting. So what the reaction of the springs now? W by 2. That's all. Now Bendman diagram is same. If it is going to be for, sir, whether Bendman diagram is same. What's the Bendman here? Now W by 2 into L by 2, WL by 4. That is same. So by replacing the rigid support by flexible supports, SFD, BMD will not change. Previously, which one is offering the reaction? Supports are offering rigid support. Now, which one is offering a reaction? So what is this W by 2, W by 2? Reaction provided by the spring. But these reactions are acting for the beam as about a constant point load. And what about this W by 2 action? This is action. How the action is acting for the spring? No, axial load. So this beam is subject to bending or axial loading. I have to consider strain energy of the beam due to bending. But here, the springs are subject to which load? No, axial loading. Axial loading. So I have to consider strain energy of the spring under which load? No, axial loading. You can use your concept of what a work done concept can be used it now. Only one axial load. Work done concept half W into deflection. Contraction of the spring. So how to find out the strain energy? Strain energy of the beam is going to be what the same. Here what this beam is under bending. Here the springs are under axial loading. Yesterday same example, yesterday bars in parallel now. Action of the block for the bars rods is about now axial load. For reaction of the rods is going to be a constant point. Same thing now. This W by the action or reaction? Reaction of the spring. This reaction is acting for the beam as a constant point load. But this is the action of the beam. What the action of the beam? Always action will be in the direction of the load. This load is downward. This load is downward means this is the action. Action of the beam under the spring will become the axial load. So sometime they will ask find out the strain energy of this now. So what do you have to do it now? Strain energy of this beam plus strain energy of the springs. Strain energy of the beam plus strain energy of the two springs should be considered now. Half P into W, half P into delta. How to find out the deflection of the spring now? Stiffness is given W by K. So this will become as what now? Half what the delta? Change in length of the spring. P upon K. But what the P value? No, W by 2. This is representing what? A strain energy of the spring. I can use it what now? This is what now? Work done concept can be used. Why you use the work done concept now? Work done concept is not valid under impact loading. Work done concept is not valid under impact loading, as well as what? A distributed loads, and more than one load is there. So here you can directly click in the work. So this is the strain energy of the spring. First spring, second spring, and strain energy of the beam due to bending. So somebody can also complete this strain energy question now. That's why I mentioned impact loading is very important for the mechanical engineers. Most of the machine components are subjected to impact load, dynamic loads. So what the overall strain energy here now? Strain energy of the beam plus strain energy of the springs. How to find out the strain energy? Yesterday, m square dx by 2 ei. So what the bendment now? W by 2 into x. Here bendment is varying. It is not a pure bending. Then how to find out the strain energy? W by 2 into x. Strain energy of AB plus strain energy of BC. For the bendment equation, W by 2 into x. Complete this now. Strain energy of AB and BC same or different? No, same. But the strain energy of AB and BC same. What the bendment equation? W by 2 into x. Here also W by 2 into x. So it will be what now? 2 times the strain energy of AB and 2 times the strain energy of each spring. Both the springs have same stiffness or different stiffness? Same stiffness. So how to find out the strain energy of AB? Integration. What the limits now? If I take a section, what the limits now? 0 to L by 2. What the bendment equation now? This is 2 times. What the strain energy of each spring? P square by 2K. But what the load on this now? W by 2. So complete this calculation now. Is it the total strain energy or neglecting? Shear force is neglected. Already mentioned, always the beam strain energy due to shear force neglected. So what the bendment? W by 2 into x. What the limits now? 0 to L by 2. But strain energy of AB and BC are same. Why now? Bendment equation is same. You have to go for the strain energy of AB plus strain energy of BC. Strain energy of AB and BC are same. Because limits are same, bendment equation same. That's why I have taken the 2 times. So what the limits now? 0 to L by 2. So what the bendment equation? W by 2 into x whole square dx by 2 ei. And what the strain energy of the spring? Strain energy of the spring. Here you cannot use the work done concept because of what? More than one load is there. But here you can use the work done concept with the pure axial loading. Half P into delta. What is the deflection of the spring now? P by K. P by K. Stiffness concept P by K. Then it is going to be P square by 2K. But what is the load on each spring now? W by 2. So complete this calculation. So now you can complete any of the questions under impact loading, impact axial loading, impact bending. Mostly you are getting this only. And so many conclusions I made it now. So many important conclusions. Under impact axial loading, impact stress can be decreased by selecting a material with lower Young's modulus, more length, and more area or more volume. But impact bending, selecting a material lower Young's modulus, more length and more moment of inertia. More moment of inertia. Or otherwise by providing a flexible support. Providing a flexible support. Rigid supports are better under static loading. Flexible supports are better under impact loading. Most of students, they will ask, no, sir, Bendman diagram. Bendman diagram will not change. You draw the free body diagram now. And so many times, this is about a constant and point load. This is a constant reaction, a constant point load, and action is about axial load. So this spring is subject to the axial, pure axial compressive load, pure axial compressive load. And this is what now? Reaction of the spring is acting as a constant point load. So now this completed, we'll take a break now. After break, I'm going to discuss the thermal stress. I'm going to discuss now. That's why this what now? This topic I discuss after strain energy. Otherwise, without strain energy, we cannot what we can do some problem, but will not realize the what is the significance of the strain energy. That's why yesterday I mentioned modulus of resilience and modulus of toughness are the two important properties of a material when a component is subjected to under impact loading. That is the what now? Shock loading you discussed now. So it's 11:45. We are going to start at 12:05. So let me directly I will start with the SFD BMD itself now. Instead of the thermal stress, let me complete the SFD BMD. SFD BMD I'm going to complete it. Deflection, then we'll see the thermal stresses next now. Because almost you have started this now. So I'm going to start after the break directly with the SFD BMD. SFD BMD today you are going to complete the SFD BMD under constant loads. So only the first chapter you are left out with thermal stress that I am going to discuss before going for the columns I am going to discuss. So I am going to complete the SFD BMD exactly at 12:05. I am going to start it now. But the basics which are discussed, they are not going to be repeated. Shear force definition, shear force sign convention, bendment definition, bendment sign convention, supports, they are all already studied. They are not going to be discussed. Directly I am going for the just now we already done it for the two beams SFD BMD. What you have done it now? For a cantilever beam subjected a point load at the free end you have done it. Simply support beam subjected a point load at the midspan. For this two you have done it now. So remaining multiple point loads, multiple constant point loads and multiple constant moments. Then how to draw it, that you are going to discuss after 20 minutes break now. Now my way of SFD BMD is completely different from all the textbooks. My way of teaching of SFD BMD is completely different. Some students are what after completion, sir, which textbook I have to refer? No textbook is going to be, this will be there now. I am teaching the SFD BMD completely from objective point of view. I am not going to write down the equation, but all the textbook they are going to draw the SFD BMD with the equation. But I will write down what now? I will directly draw the SFD BMD without any equations. If necessary, then only I am going to write down now. Sir, when it is necessary, that I am going to discuss. So almost 70 to 80% of the questions I am going to draw the SFD BMD based on the conclusions what you are going to discuss. That's all. Already some conclusion, number of vertical lines, that all you are going to discuss. If necessary, then only I am going for the equations. And if you use this method, then only you are able to complete the questions in objective examination. So okay, we'll meet it at exactly 12:05.